So my name is Eric Butler, and today I'm going to talk about how we can have some fun with native code on Android. So this project started for me about 7 months ago. I had just moved from San Francisco to New York City, and I was setting up a new apartment. So I picked up a new TV that runs Android, of course, and I was unpacking some boxes, and I found this thing. And this is a Bluetooth controller that is designed to look like an old Nintendo controller. And so I wondered, could these two things work together? So I charged this up, paired it with a TV, and sure enough, it worked. I was able to use the controller to navigate through the Android TV menus and to play some games that I found on the Play Store. And so while I was using this replica controller, my next thought was, could I use this to play old retro video games on the TV? So I went to the Play Store and searched for emulator apps. And I found a lot of apps that had a lot of problems. Many of the apps were designed for a phone, so they would have touch controls on the TV that you couldn't do anything with. They had poor performance. Some of them didn't work with the controller at all. A lot of UI problems and very complicated setup. I found one app that had like a 40-minute YouTube video explaining how to use it. And so I started to wonder, could I build something? And what would my dream app look like? So thinking through the requirements, I knew that I wanted an Android TV style user interface that would feel at home on the TV and be designed for sort of that 10-foot experience. I wanted something that would work well with game controllers out of the box, like this controller that I had here. I was looking for the ability to load games from the cloud rather than take up the limited storage that was built into my TV. And I wanted an app, a single app that could support all retro consoles without any additional downloads or configuration. So thinking through these requirements, I knew that I could build an Android TV interface using the leanback support library from Google. I learned that the standard Android input APIs can be used to handle game controllers, so adding support for a controller is very similar to supporting a keyboard. For loading games from the cloud, the Google Drive and Dropbox SDKs are already there, so I figured I could use that. But maybe I was getting a little bit ahead of myself, because I actually knew nothing about emulation and how I was going to play these games. So I did what anyone might do and go to Google, and I put in what I thought was a pretty unlikely query, which was looking for an open source retro video game emulator library. I had pretty low expectations, but Google delivered, and I found this. This is a project called libretro. Libretro is a single API that abstracts many retro consoles. It's specifically designed to make it easy to write a front end, which is what I was looking to do. It's free, it's open source, it's well documented, which is awesome, and it's designed to be a lightweight cross-platform C library. So this sounded perfect, right? Well, there was just one problem. I've been doing Android development for a long time, but I've never worked with native code on Android before, and I had no idea what to expect. So something that I learned is that the mechanism for interfacing between a high-level language like Kotlin and a low-level language like C is often referred to as a foreign function interface, or FFI. Some common implementations of FFI includes Python C types, C#, pinvoke, and Java Native Interface, or JNI. JNI is the default choice for Android. It's part of the NDK from Google, the Native Development Kit, and it's what I assumed I would be using for this project when I started. Now, I like to think of high-level JVM code as sort of being the world that we're all used to. It's safe, we know what to expect. And meanwhile, native code is the upside down, where anything can happen and there are monsters everywhere. So I went into this project feeling very intimidated, and let's explore together how scary this really is. So let's start things off with a very simple C shared library. This library has one function that takes in a name, and it prints the name to the console and says hello. We can call this function using Python C types very easily. The first thing we do is import the package. We specify the library we'd like to load, and then we call our method. It's that simple. Doing this from C# is also pretty simple. we can import the interop services namespace, create a function that matches our C function using the extern keyword and no method body. We use the DLL import attribute specifying the name of the library, and then we can call our method. So moving over to Kotlin and the JVM, I very naively wondered, could I just do the same thing? So I define a function using the external keyword, which is equivalent to the native keyword in the legacy Java programming language. We can then tell the system to load the native library and call the method. Now, unfortunately, this does not work, and I quickly learned why. It turns out that JNI is not able to call standard C functions directly. So if we go back to our simple C shared library, we have to actually wrap our function in another function that's specifically built for JNI. And now our simple C library isn't so simple anymore. And one thing you'll see here is that we need to explicitly convert between the Java type, in this case a string, and the type that the C program expects, which is a char array. So with this change, if we go back to our Kotlin code from before, we can see that it works. And that's great. But the idea of having to write so much C++ boilerplate for this project was really not very appealing, especially knowing that both C# and Python can do this all automatically, as we just saw. So I went back to Google with yet another unlikely query, this time wondering, is it possible to call native code from Java without using JNI? And once again, Google delivered, and this is how I found a project called Java Native Access, or JNA. So letting JNA's README describe itself for a moment, JNA provides Java programs easy access to native shared libraries without writing anything but Java code. No JNI or native code is required. It goes on to say this functionality is comparable to C# pinvoke and Python C types. So this sounded like exactly what I was looking for. And one note, anytime you see the word Java, just replace that with Kotlin in your head. So digging into some of JNA's features, I learned that it can automatically map between C functions and JVM methods. It can convert C types to and from JVM primitives. If you have a struct in C, you can convert that automatically to and from a JVM class. And there's also explicit support for C code that expects a function pointer so that you can implement a method in your high-level language, Java or Kotlin, and use it as a function pointer in C. And we'll see in a little bit why that's really important for this project. So digging in to the JNA library, I found that it's actually pretty big and pretty complicated. But the good news is there's only a few types that really matter for this project today. The first is called library. This is a base type for an interface that contains all the definitions for your native library. So what this looks like is an interface that extends from library, and you list all of your native functions here. And this is done instead of using the external keyword for JNI in Kotlin or the native keyword for JNI in Java. The next class is called native. And this has a bunch of static methods for loading native libraries, configuration, some other tasks. The primary function is loading native libraries. The way this is used is you call native.loadLibrary, you pass in the name of your native library, and you pass in the class of the interface that we just created. This then returns an instance of that interface, which you can then call methods on. The next type is called structure. And this is what allows JNA to automatically map between C types and JVM classes. You simply create a class that extends from structure, and then define the fields with the same types as your C code. Because we're using Kotlin, and because there's some reflection happening under the hood, we do need to use the JVM field annotation here. One other thing we need to do is override this method called getFieldOrder, and this is required so that JNA knows how these fields are laid out in memory, because it can't reliably get this information from the reflection system. Next up is callback. And this is what allows you to implement methods in C or in Java or Kotlin and use them as callbacks from C code. This works by creating an interface that extends from callback. You define one public method with any name on this with a signature that matches your C code. You can then use this callback anywhere, like for example, in a function parameter here. And then you would implement this interface exactly as you would expect by creating an implementation and overriding the method that you've created. Finally, we have pointer. Pointer is used for accessing arbitrary memory, and it can be used anywhere that you might expect. For example, a method argument, a method return type, and also as a callback parameter. Pointer has functions that allow you to read data as different types. So for example, you can ask for a string, an int, a long. You can also ask for an array of bytes, and you can read data from memory into an existing buffer that you've set up before. And later we'll see how these are really useful for this project. I'd like to touch a little bit on performance, because this is something that comes up a lot when looking at alternatives to JNI and other ways to do these things. If you read the FAQ, you might see something pretty scary about JNA being 10 times slower than using JNI. But it's important to note that this is the call overhead and not the total time of execution. What that means is, if you have some C code that goes off and does a bunch of work and then reports back, the total execution time is not going to be 10 times slower. There's just going to be a slower call overhead when you initially set up that method. And in many cases, the ease of programming is going to outweigh the difference in performance. Importantly, I think it's important to follow the principle of first building, then measuring, and then optimizing, so that you don't waste time optimizing the wrong thing. So if you write something using JNA, and you actually find that JNA is your bottleneck, you have the option to incrementally rewrite using JNI later. And I think it's important to note that using JNA does not preclude you from using JNI. You can mix and match, and you can rewrite any slow code if absolutely needed. So let's dive in and try this thing out with some code. Here's our simple C shared library from before, and we've removed all of that ugly JNI C++ code from it. Now we have our Kotlin code, and this is where we unsuccessfully tried to call our library using JNI. So let's look at how we can convert this into using JNA instead. The first thing we need to do is import the package. Next, we need to create an interface that extends from library, and this will hold all of our definitions. Now, we just move our function definition into that interface, and we remove the external keyword, because that is specific to JNI. We move from using system.loadLibrary to use native.loadLibrary instead, pass in both the name of the library and the class of our interface. This will then return an instance of that interface, which we call our method on. We can test this out from the terminal pretty easily by using Maven on the command line to fetch the latest JNA jar. And then we can run this code as a Kotlin script, and it works. So now, I think that the last missing piece of the puzzle for my dream app is starting to come into focus. It looks like we might have a solution for this last thing, which is a combination of libretro and JNA. So let's take a look at libretro now. While I was reading about libretro, I basically found four resources that together painted a pretty clear picture of how this library works. The first was the documentation. The library was surprisingly well documented. There's an integration guide as a PDF, and also pretty extensive web documentation. Between the two of these, I was able to get a pretty good high-level understanding of how this system works. Next up was the header file. It turns out the entire library is defined within a single header file. I saw that it was over 2,000 lines long, which was a little bit scary for just function definitions, but I quickly learned it was actually mostly comments, and so that's pretty great. In the end, there's actually 25 functions and 31 structs, and don't worry, we don't need all of those for this demo, so I'm not going to be going through them one by one. The next thing that I looked at were the libretro cores. And a core is an emulator that has been ported to this common API. So for example, an emulator for Super Nintendo, for Sega Genesis. There are many of these out there, and people in the open source community have been porting them to work on this common API. Libretro calls those cores. Looking at the source code for the cores was really useful to see which APIs were actually needed. So going from those 25 methods earlier, I was able to narrow it down quite a bit by seeing what code was actually implemented. In general, what I found was that the code for these cores, the libretro specific code, was in a single file. And so, for example, the first link here is the libretro code for a Super Nintendo emulator, and the second URL is the libretro code for a Sega Genesis emulator. And by having all that code in one file, it just made it really easy to understand what was going on. Finally, there were some existing apps that were already integrated with libretro. And this was really useful for filling in gaps in the documentation. The three apps that I looked at were RetroArch, Phoenix, and GNOME Games. RetroArch is actually the reference implementation of this library. It's written by the same people who wrote the library. Phoenix is a little bit newer. It's written in a combination of Qt and C++. I found the code really easy to read, very modern. And I think GNOME Games is actually the newest of the three, written in a combination of C and Vala, which is a C#-like language for the GNOME platform. And it was also a very useful resource. So now, putting together everything I've learned from all these resources, I found that there are pretty much three things that I need to do with this library. The first thing I learned is that the library is callback based. So the first step is to initialize callbacks. Next, we need to actually load our game, and then we run the game loop. So let's dive into these three things. There are 4 callbacks that are required for libretro. The first is called the audio callback. This is called once per frame of the game, and it has a pointer to audio data that needs to be played. Video is very similar. It's called once per frame as well, and it has a pointer to video data that needs to be rendered on the screen. Next, we have the input callback. This callback is called once per button per frame, and the front end returns true or false depending on if this button is pressed. So if you have a controller with 6 buttons, you'll have 6 callbacks per frame with different parameters specifying which button the system is querying. Finally, there's a callback called environment. And according to the documentation, this is mostly unused. It's for obscure functions. So let's just not worry about that right now. Moving on to actually loading a game, there are 2 ways that this can work. The first option is that the core is going to load the game. So we, as the front end, just give the core a file path. And this is the path to the ROM file. The second option is that the front end loads the game and specifies a memory pointer to where the game has been loaded, and then the core will read from there. Finally, moving on to the game loop, the important thing that I learned here is that libretro runs 1 frame at a time, and it's up to the front end, which is what I'm working on, to actually maintain the correct frame rate. And so that's something we're going to have to worry about a little bit later. So now let's look at pulling these 2 technologies together. And the first step is going to be to write bindings, basically taking the C API and creating equivalent classes for any structs and method definitions for any C functions for all of the functions that we need. The next step is going to be to implement all the callbacks. So audio callbacks, video callbacks, and the input callback. And then finally, we're going to have to call some functions to tie it all together. While I was researching how to build JNA bindings and how the API works, in addition to the documentation, I found this thing. This is a tool called JNA Orator. And what this does is you can point it at a C header file, and it will output JNA code automatically. I found that it actually worked quite a bit better than expected. In the end, I ended up writing the bindings by hand, partially because I wanted them to be written in Kotlin, but also because this wasn't quite perfect, but it served as a really useful reference. So anytime I wasn't sure about something, if the JNA documentation was unclear, I would try plugging it into this and see what it came up with, and often could figure out what I was doing wrong. So it's a useful tool if you're going to be using this. Okay, so let's actually look at how we can build something real. The first thing we need to do is add JNA to our build.gradle. If you're wondering where your native libraries are actually going to live, they can go into the JNI libs directory. Even though it says JNI and not JNA, it works. So now that we have our dependency in place and we have the native libraries somewhere where JNA can find them, let's look at actually writing some bindings for this real library. The first function is called retroinit. This is very simple with no inputs and no outputs. And this is what the JNA wrapper looks like. It's even simpler than the example from before. Next, we have something slightly more complicated. The first thing you might see about this function is that it returns a Boolean, but more importantly, it takes in a struct as a parameter. The Boolean will be handled automatically by JNA. It will get converted into a Java or Kotlin bool, no problem. In order to use this struct, which is defined in the C header like this, we need to create a class that extends from structure. We need to define the fields matching the C definition. And one thing that you'll note here is that char star can automatically be represented as a string, and JNA will handle that automatically for you. We then still need to override that get field order that I talked about earlier. And then finally, we can add this function to the library. And this is the function we're going to call to load the game ROM into memory. Next, we have the first callback. This one's for audio. So this is what the C definition looks like for setting the audio callback. This one does not take a struct as a parameter. This actually expects a function pointer. The signature for that function pointer looks like this. It has two arguments, a pointer to some data, and some information on how long that data is. We can wrap this up in JNA like this by creating an interface that extends callback and creating one public method with the same signature. And here you'll see that we're using pointer because there's no other type that can be used here. And of course, we add it to the library. The video callback looks very, very similar. Again, we have a method that expects a function pointer. The signature for this C function is a little bit more complicated, but it's basically the same idea. It has a pointer to some data, and then it has some width information, some height information, which allows us to know how much memory we're going to read. Creating the JNA wrapper, again, is very similar to audio, and again, add it to the library. Finally, we have the input callback. And this one's pretty important, because after all, this project started thanks to this game controller. So it'd be nice if we could actually play our game. The function signature looks like this. It has information about which button was pressed, which device that button press came from, and which player we're polling information about. So once again, we can create the JNA wrapper and add it to our library. For input, we also need a few constants, so we can define them just like this. Finally, we have the method that actually runs the game loop. Nothing fancy here. So a quick review. Here's everything that we have so far, and we can see that things are starting to come together, and it also fits all pretty nicely on one slide, which is nice. We have callbacks for audio, video, and for input. We have a way to load a game. We have a way to initialize the library. And we have a way to run the game. So it looks like step one is just about done. Let's move on to the next step to actually implement the callbacks. And this is where the integration with Android is actually going to happen. So first, starting with audio, we create an implementation of our callback that we defined earlier and override the invoke function. Now, the first thing that we need to do here is figure out how many bytes we actually need to read from memory. The frames argument here is number of frames, which is not the same as number of bytes. So knowing that this is 16-bit stereo audio, we can figure out how many bytes to read. For the purpose of this demo, I've hard-coded that, but all of these values are available from the libretro API dynamically. So the next thing we can do is read that many bytes from memory. And we can use the pointer.getByteArray method that we talked about earlier. We specify an offset of 0 to start right at the pointer and specify the number of bytes that we want to read. So now we have a buffer full of audio data. So what can we do with that? Well, the cool thing is we can use the standard Android media APIs. We create an audio track, specify some options. Again, I'm hard coding a few things here, but there are ways to dynamically get all of this information. And then we can simply write the buffer to the audio track and call play. So that should take care of audio. Let's move on to video. The video callback is a little bit more complicated, but basically the same idea. Once again, we're going to calculate how many bytes we need to read. And then we're going to read the data into a buffer. Now, you'll notice here that I'm creating a buffer myself and then using pointer.read to read the information row by row into the buffer. The reason for this is that the video data is not contiguous in memory. So if you read from the start to the very end, you actually get a bunch of blank black pixels in your video. This is an example of where looking at an existing front end was really helpful. There's no way I could have figured this out on my own, but I was looking at the source code from one of those other apps that I showed earlier, either Phoenix or RetroArch or GNOME Games, and that's how I figured out what was going on with this. So the next step is we can create a standard Android bitmap and copy the pixels from our buffer into that bitmap. Finally, we can set that bitmap onto an image view. Now, in a real application, you would probably want to use a surface view here. And in fact, this slide has several sins against graphics programming. In general, you want to avoid allocating a lot of memory when you're rendering data. You want to avoid copying bytes as much as possible. But for the purpose of this demo today, this actually works surprisingly well. And once again, I'm hard coding some information about the pixel format, but that information is also available from some of the other libretro APIs. Finally, let's take a quick look at input. We can override this method, and this method will be the one that's called per button per frame. The first thing we'll do is check that the port is 0, and otherwise we'll just return. The port specifies which player for a local multiplayer game console that we want to query about. So if we wanted to support local multiplayer in the future, this is where that code would go. But for now, let's just keep it simple and support only one game controller. Next, we want to take a look at the device type. libretro supports many types of devices, not only game controllers, but also mice and keyboard, light guns, other things. But for now, let's only add support for game controllers. The next thing we need to do, we need some way to keep track of which buttons are currently pressed. For now, a simple set, a mutable set, will do. We can then take a look at those constants that we defined earlier and map between the libretro device IDs and the Android key events. So I mentioned earlier that game controllers are handled very similar to a keyboard. And so this is an example of how under the standard key event, which you may have used for other applications, non-gaming applications, we have key codes for start, for up, down, left, right. So we can map between what libretro knows about and what Android knows about and see which buttons are pressed. So now we need some way to actually keep track of which button is pressed. And a quick and easy way to do that is to override the dispatch key event method in the activity and simply add and remove from the set when buttons are pressed and released. So now, it looks like we're done implementing callbacks. Let's move on to the final step where we're actually going to tie this all together. As we saw before, the first thing we want to do is call native.loadLibrary. In this example, we'll specify a Super Nintendo emulator, and we'll pass in this library interface that we've been incrementally building up. Excuse me. Next, we're going to set up all the callbacks that we just defined and initialize the library. So we've got audio, we've got video, and we've got input. We then want to actually load our game. So we'll create an instance of that class that represents a structure, and we'll set the path to be a game that I put on the SD card, in this case, Super Mario All-Stars. We'll then pass that struct into the load game method. So finally, I mentioned earlier that libretro runs one frame of the game at a time. So we'll start a timer that calls this method 60 times per second. So let's give this a try. Here's the same code running in Android Studio, and let's hit go and see what happens. I put it into a button click handler, so we'll click on the button. Something went wrong. You know what? I probably just made a simple typo somewhere. Let's just go into logcat and see what happened, and oh my gosh. So what is this? So when you're working with native code, you won't get the nice human-readable stack traces that you're used to. Instead, you'll see something like this. And this can be pretty scary if you're not used to it. The good news is that Android has a pretty great native debugger. So what we can do is we can move into the Edit Run Configuration dialog, and we can change the debug type to be native. Then, when we run this again and reproduce the crash, the debugger will kick in, and we can pretty quickly see what went wrong. Here we can see that the C++ code is trying to call a function called environ callback, and it's actually null. So it looks like that documentation from earlier that told us that this environment callback isn't important was actually wrong, and it is quite important. So let's just go in and fill in that one missing piece. Just like before, we will create JNA bindings for the C API. The callback function signature has two arguments, a command and a data pointer, and it's assigned with a function called setEnvironment. So let's just slide that in to our bindings, and now we have the bindings are actually complete, and it still kind of fits on one slide. We do need to actually implement that environment callback. However, it doesn't need to do anything, so we'll just have it return false. Back to our initialization code from earlier, we can just slide that right on in. So now, let's give this one more try. So up until this very moment, I had no idea if any of the work that I had been doing was actually going to pay off. So this was a very, very exciting moment. I was able to see video, hear sound, and also play the game. And this is a great game that I definitely remember playing a lot when I was younger. So I felt really, really good about this, but I wasn't quite done. Remember, one of the goals here wasn't just to build a Super Nintendo emulator, but to build a system that could play to build an application that could play games from many different systems. And so I wondered, what about Sonic? So going back to our code from earlier, I tried changing, up at the top, we have the Super Nintendo emulator library, changing that to instead be a Sega emulator library, and changing the game, instead of being Mario, let's try Sonic 3. So once again, here's that code running in Android Studio. And this time, I'll try turning up some sound, but you only will be able to hear it if you're in the front of the room. And so sure enough, Sonic worked as well. So it seems like libretro has delivered on its promise of being a multi-platform library. And this was very exciting. I've tested not only Super Nintendo and Sega, but also the original Nintendo, Game Boy Color, Game Boy Advance, and MAME, which is the arcade game emulator. Does anyone remember this game? It was lots of fun. It was very hard. So back to the beginning, I was talking about my dream app. And it seems like this is not really a dream anymore. And I've been working on taking the prototype that I just demonstrated and turning it into something real. And this is what it looks like today. The code name is Odyssey. It has a basic Android TV user interface. It supports 7 different platforms, and it has controller support. It can save games and load game saves, and it can play games from a HTTP server. In the future, I want to add support for many more consoles. I want to make the UI a lot better. I definitely would like to add support for multiple local players. I think internet multiplayer is totally possible and would be really, really cool. We still need to add the cloud storage support. Someday, we might even be able to stream right to Twitch or YouTube. So the source code for this thing is on GitHub. If you're interested in games and want to check it out, please do. Let me know if you want to help contribute. And I hope you've learned that working with native code doesn't have to be scary. It can actually be a lot of fun. So thank you for coming.